you very much that you are with us. Let me introduce our speaker today. This is Professor Andrey Dorogovtsev. He is the head of Department of Theory of Random Processes at the Institute of Mathematics, National Academy of Science of Ukraine. Professor Dorogovtsev has made his PhD in 1987 in Kiev, and his supervisor was Anatoly Skorokhod. I hope that everybody knows this name. Yeah, and Professor Dorogovtsev made his habilitation in 1991, again in Kiev. And since 2004, he is a professor at the Institute of Mathematics, National Academy of Sciences of Ukraine. Since 2021, he is a corresponding member of the National Academy of Sciences of Ukraine. He is also the member of American Mathematical Society and European Mathematical Society. He has published 5 monographs and more than 100 papers. And his scientific interests are probability theory and stochastic processes, namely stochastic integrals, stochastic calculus of variations, and the Malevin calculus, stochastic equations, measure-valued processes, random operators, Markov processes, local times, multiplicative functionals, probability theory on linear topological spaces, and stochastic flows. And hopefully we will learn something about this big branch of stochastics from today's talk. So Professor Dorogovtsev, you're welcome. Could you please share your slides?
Thank you very much for such a kind introduction and for the invitation to make a talk despite of the middle of the summer. I organized today talks as a descriptive talk. I decided to choose some part of the mathematical investigations which which we hold in our department, and talk is organized as follows. It is called Dynamical Systems, Flows, and Stochastic Analysis. Firstly, we will discuss how can we describe the complicated dynamical system. What I mean, let me. Usually, when we discuss the mechanical system under random perturbations, we commonly use the language of stochastic differential equation, where the deterministic term like A xt dt is corresponding to the external forces which are acting on the system, and stochastic term which can contain not only differential of the Wiener process but more complicated processes like martingales, Poissonian measures, and so on, describe for us the influence of the random media. There is a well-known, well-studied, and well-developed and deep theory of solution to stochastic differential equation, but the common point of view is that it describes the motion of one particle under external force and random perturbation. If we are looking for the system of the particle, moreover, for the mass distribution of the system of the interacting particles in the random media, we have to involve such different mechanisms as, for example, diffusion, when one particle can turn into the diffusion cloud, for example. Then we need some partial differential equation like heat equation, also with stochastic term, and we get a well-developed theory of stochastic partial differential equation. Also, one can consider the system of interacting particles, which leads to mean field equation in such a way that particles interact one with others. For example, like here you see the sum, which is correspondent pairwise interaction, but also contain the noise individual for every particle. By the way, now such a model which leads in the limit to Makin-Vlasov mean field equation are very popular in financial stochastics, because it is more or less reasonable that every particle, every player in the market has individual noise. These are well-known descriptions which we can see when we start to think about the interacting particle in the random media. What are the popular mechanisms? Deterministic forces, some random perturbations, and there are a lot of different things related to boundary conditions. For example, reflections, if we consider the particles which move inside of some domain. Coalescence, we will see further. It means that particle can coalesce after the meeting. Splitting, one particle can turn into cloud, for example, as I said, or at least into particles, and so on. So there are a lot of different infinitesimal laws which we have to take into account when we are trying to describe the system of the interacting particles. So let me show some example. This is well known, but very important for us example. If we consider a stochastic differential equation with the discontinuous coefficient, like Tanaka equation, it is very simple, then it is known that it has no strong solution. If we consider noise, if we consider the pair, the weak solution pair W and X, then we have a strong inclusion of sigma field generated by W to the sigma field generated by X. Further, if we consider stochastic differential equation on the manifolds, for example, if we have some system of the particles with restriction, then we have to put some very special conditions on the coefficients in order to get the motion exactly on the manifold. Also, let me show you the very simple example of the system with interaction, but this example is interesting historically because it arose at the work of Helmholtz. It is approximations of the Euler equation for the fluid motion, and here VI, this is a position of the infinitesimal vortices, and we see that we have exactly equation with interaction. The infinitesimal increment of the trajectory of one vortex depend on the other one. Now let us consider the first equation, which was derived for interacting particles system, and it originally was proposed by Peter Kotelenets in 1995. This equation is the following kind, as you see on the top of the slide, and this is equation for several heavy particles. Even due to Skorokhod, the weight of the particle, which has coordinate xj, xi of t, can depend on the time. So we have such an equation which contains in the coefficients mass distribution of the particles. But it must be noted that in Koteleni's work, it was considered like a system of the special kind of stochastic differential equation. What is interesting that the noise was common for all particles. And in 1997, I proposed in our work with Peter Kotelenic the following form of stochastic differential equation with interaction. Here you see that it is a stochastic differential equation with for infinitely many for continuum processes together. The processes x, u, t start from the point u, every point of the space. And mu t is the image of the initial mass distribution, mu 0, under the map xt, and mu t is present in the coefficients b and sigma. Also, it must be noted that here we use not the one Wiener process, but stochastic Gaussian measure with independent values on the disjoint sets on the product of the space and time. You see W capital from dp dt. And it is important because it reflects the following thing, that a particle in different points of the space are interacting with more or less different molecules of the media. So the influence of random measure must depend on the position of the particle. But this is not the mean field case where every particle have independent noise from other. Here only a partial set of names of my student and colleagues from department who continue investigation in this direction. Let me show you examples how we can turn Helmholtz equation, for example, in equation with interaction. You see, it is very easy, like a trick. We just raise this index I near V in the left-hand side. And we have the family now continuum family of equations, which are government, of course, only heavy particles, but we will discuss this. Also, let me show you the well-known example of equation with interaction, which comes from applications. This is Kuromoto's system of connected oscillators. And you also can see that it can be considered as equation with interaction very easy. It just writes this index I in the left-hand side. Yeah? What is the main features of the equations with interaction? The coefficient contains the mass distribution mu of all particles, which allows to take into account interactions between particles. For example, if we have the coefficients of such integral form, it describes a k-type interaction, because if we consider the term which is related to fixed r and u1 uk minus 1, then the term will have the form fk r u1 uk minus 1 multiplied on the weights which mu gives to the point u1 uk minus 1. So it is related to k-type interactions in the potential fk. Also, it is interesting that mass distribution mu let me recall you the form of the equation with interaction. You see it here. Mu zero can be continuous measure. It can have density with respect to Lebesgue measure. Even in this case of Helmholtz equation, one can consider the mu t as a continuous distribution. So then we will have, instead of this sum, we will have integral, like you see this coefficient b mu, r mu. This is the next interest feature. And also, it is interesting to see that equation with interaction describe motion of particles starting from every point of the space, even those who have zero mass. Of course, one can say that if we have heavy particles, firstly we will solve our system for heavy particles, and then these heavy particles will determine the destiny of the particles with zero mass. Yes, it is true. Now, this is one approach. As I said, in the first part of the talk, we will discuss different approaches to description of the interacting particle system with random perturbations. Another one approach arises exactly from Tanaka example, and let me say that in this approach, we will discuss the random measure on the space of trajectories of initial system. So first of all, we need to give the formal definition. What is the adapted random measure? We consider random probability measure on the space of continuous functions, 0, 1. W is Wiener process. Of course, it can be a Wiener process even Hilbert valued. So the noise is can be as complicated as you want. But we consider the flow of sigma fields generated by the noise, and we say that mu is adapted to the flow or to the noise if for finite dimensional integrals relatively to our random measures, these finite dimensional integrals are random variables, we have the following relation that such random variables are measurable with respect to ft. If we take finite dimensional distribution of mu up to the moment t. This is a natural definition, but we have to produce it. Then let us consider the example. We already mentioned that stochastic differential equation not always have strong solution. So not always we have a pair x and w which satisfies the integral form of the equation and such that x is a functional from w. So in the case when we have only weak solution, it is natural to consider the conditional distribution of x with respect to the initial noise. In our case, with respect to w. This conditional distribution is a random measure on the space of trajectories, in our case, in the space C01. And actually, it is adapted. So one can say that there are some cases when we have no strong solution in usual sense, but we have a strong measure-valued solution because in good cases this conditional distribution is unique. Example. Let us consider Tanaka equation, for example. In this case, this equation has no strong solution, but it has unique weak solution. So we can consider this conditional distribution of x with respect to w, and ask what is it. And now it can be described very easy. Suppose that we have this Bernoulli sequence epsilon n, which is independent from w, and Fn be the sequence of a Scarchinal W enumerated in some order. Then mu has the following kind. If we fix W, this is just distribution of this sum. It occurs that this random measure mu, if we consider it as a strong solution, must satisfy so-called Hopf equation. Hopf equation arises in fluid mechanics, and I will say a few words about it later. But for us, this equation is simply equation for finite dimensional characteristic functionals of our solution mu. And if we consider this equation relatively to t n plus 1, you see we will get the usual more or less stochastic differential equation. You see TW here, eta terms 1/2 of lambda n plus 1 and so on. So one can prove that mu satisfies such equation, and now such solution is, to this equation is unique. It must be said that the idea of such solution arises in the well-known book of Vyshek and Fursikov, devoted to fluid mechanics, and they propose to consider such kind of measure-valued solution to Navier-Stokes equation in case when we are not able to prove the uniqueness and existence of the solution, when we are not able to prove the good properties of the solution. So they call it such measure-valued solution by space-time statistical solution. Also, it must be noted that this random measure mu is Markovian, and it has kernel KST, which can be defined as follows. And in this sense, this random measure, the adapted measure-valued solution to stochastic differential equation, coincide with the kernel solution in the sense of Lejeune and Raymond. Again, the same usual equation as for dynamical system arise in this framework. This is the second one approach, and the third one, which I want to discuss today, is stochastic flows. If we consider X row a complete separate metric space and define and consider on this X family of random mappings such that for non-intersecting interval of the times, these random mappings are independent. For any ST and R, the shift of the random mapping phi ST, phi S plus R, T plus R are equidistributed, so it is time stationary in increments. And we have evolutionary property, but in weak sense. It means that for fixed U, we have such relation except of the set of probability 0, but the set probability 0 can depend on S, T, R, and U. So this is not a random dynamical system in strict sense, not as it is considered in a book of Ludwig Arnold, for example. We call this set of mappings stochastic by the stochastic flow. Also, despite of the some non-rigorous words, we will say that XUT, this is mapping which start at the time 0, the point U. Also, this family will also call stochastic flow. Examples. If we consider our space X equal to RD and have a stochastic differential equation with a good coefficients, then we know that it generates the stochastic flow even for good A in B. We have a stochastic flow of diffeomorphism. More complicated example we get from Harris, and it is the Harris flow is a family of Brownian martingales with respect to common filtration. It means that every XUT is Brownian motion with respect to the same filtration, and X is order preserving. It is natural when we consider the family of particles on the real line, because they cannot jump one over another. And we suppose that the mutual quadratic characteristic of our martingales has the following kind. Its differential depend only on the difference between the positions of the particles, and phi must be some positive definite function. Here I said that this example is more complicated due to the following reason. It is known that even for good phi, for example, phi can be Fourier transform of density of stable distribution. It can occur, the coalescence can occur in our flow. So, in contrast to the example 1, in example 2, two particles which start from the different points of the space can coalesce in the finite time, and then they move together up to infinity. This is a so-called coupling by love. And the last one example, but very well known and very illustrative from different points of view, is the Arakia flow. It formally can be described as a partial case of Harris flow when we take this positive definite function phi as simple as possible. It is only the indicator function of the point 0. So it is equal to 0 for any value from the real line, not equal to 0, and at 0 it takes a value 1. In this case, we see that up to the moment of the meeting, the differential of the mutual quadratic characteristic is equal to 0. And this leads to the following non-formal description of the Arakia flow. This is non-rigorous, but sometimes helpful, that it consists of Brownian motions, which start from every point of the space, independent up to the moment of the meeting, and after meeting move together. This is again the features. You remember when we consider the equation with interaction, we consider some special features of such equation. Here the same, we do the same, and the main features which leads to very deep and interesting results are the following. It occurs, it follows from the definition that the law of one-point motion does not determine the flow. You see, every Harris flow, for example, consists of Brownian motion. So if one looks only one fixed particle from the flow, it moves like Brownian motion, and if we were sitting on this particle, we will not understand the structure of the flow completely. The second one is possibility of coalescence. It leads to organization of the clusters in the flow, and also to natural leads to the third one feature, that the map xt in comparison to stochastic differential equation can be discontinuous. It can be even step function. So these are the properties, and now let us see the questions, because usually when we discuss the description of some dynamical system, of course we have a set of natural questions which arise probably from ancient times, when people without formal definitions consider dynamical systems. They want to know what will happen. But when we consider the stochastic flows, some other new questions arise. For example, rigorous construction of stochastic flow in every case is a difficult question. Also, what are the properties of the mappings with respect to time, with respect to space? Related question is description of Markov process in the space of mappings related to stochastic flow. Here it must be mentioned that maybe Darling was first who tried to organize stochastic flow in general space, and generally we have a lot of questions related to measurability. It published a small book in, it seems, 1984, non-homogeneous stochastic flows or something, and it is very interesting relatively to questions of how to formally define the stochastic flow consisting of general mappings, non-continuous, and so on. And the last question is also very important. You remember the situation which we mentioned today about the weak and strong solution to stochastic differential equation. So in general, we can start from the good formal description, like we have external force, random perturbation, or just random perturbation, but finally we get the situation when the solution has much more rich sigma field flow than initial noise. So when we discuss the stochastic flow, it is natural to ask what happened in the presence of coalescence. What is the structure of the noise, structure of the flow of sigma fields generated by the stochastic flow or X, or by this family of mapping phi? In the work of Watanabe and Cyrilson, you can find a very good examples which shows us that the noise can be can have that the flow of sigma field can have completely different properties in comparison with the flow of sigma fields generated by, for example, good Gaussian martingale. Now let me summarize the first part of my talk. So we see three approaches which are which we consider in our group related to equationless interactions, random measures on the space of trajectories, and stochastic flow. Now let me present you some examples, only examples of the results which we can get there, because of the set of statements is too large just for even for formal repetition during the seminar talk. So I tried to find such examples which reflects the features which we mentioned and which reflects new questions which we can pose about these objects. So let's start from equation with interaction. You remember, I will not came to the slide, but you remember that the main feature in this equation was that we have in the coefficients the presence of the mass distribution of all systems. So one can say, okay, that's not a problem. Just define some distance on the set of measures. We consider probability measures, so there are a lot of distances, and say, let coefficients satisfy Lipschitz condition with respect to this distance, then everything will be okay. Yes, if you work with global Lipschitz condition, then more or less one can say that there is a unique strong solution to equation with interaction. But you remember that there are another set of conditions like local Lipschitz property and linear growth. And it occurs that here the structure of the set of probability measures, even on the real line, or in the finite dimensional Euclid space, came into play because for good distances, like Wasserstein distance of any order, like moment distance or distance related to convergence in probability, we have that the set of measures is non-locally compact. And this leads immediately that one can invent the example when under this linear growth with respect to coordinate and local Lipschitz property, we have not a unique solution. It was invented by my PhD student, Maria Karlika. Another question. We already discussed that we are interested when we consider arbitrary dynamical system in its long-time behavior description. But when we have the system of interacting particles, let us think what we can expect. For example, if you recall this Helmholtz approximation equation, people studied numerically very well, and formally it must be said that, for example, such a great person like Vladimir Arnold wrote an article about these Helmholtz approximations. Then they discovered that it occurs that these vortices do not go to one point at infinity, but they keep some special structure. And this special structure, like they equidistributed on the some circle, and this circle is rotating. So the same happened with Kuramoto equation. For Kuramoto equation, we also cannot expect that all this oscillator will stop at some point. No, but they became to oscillate more or less with the same phase. It means that we have something like partial synchronization. This is a name from applied mathematics. So we produce the following definition: a family of probability measures is called shift compact if there is a family of vectors such that the family of shifted measures is weakly compact. This definition covers the mentioned cases, we don't think that the mass distribution of our system of the particles will freeze at infinity. But we are looking for such cases when this mass distribution will more or less concentrate near the moving center. This moving center is V indicated by I. So we produce such definition, and we have the theorem which gives us the condition under which the family of mass distribution mu t is shift compact with probability 1. Now let us go to stochastic flows. I will consider the third approach because the second one is more complicated in description. Even, for example, we need stochastic variant of Fubini theorem with respect to adapted random measures. We need theorems adapted the structure of random measures. So it is not so illustrative as the first and third one. Now let us think about stochastic differential equation with respect to this Wiener measure in space and time. And we suppose that phi indexed by epsilon. This is, by the way, this is a window which reflects how our particle interact with random media. And we suppose that a support of phi belongs to the interval minus epsilon epsilon. So when epsilon tends to 0, the support of phi tends to just 1.0. From this point of view, it seems that particles placed in different points of the space are interacting with the different molecules of the media and move independently up to the meeting. So it is natural to expect that we have the following. The endpoint motions of x epsilon converge weakly to endpoint motion of the Arakia flow when epsilon tends to 0. It can be proved, and I must say that at this time I didn't know anything about Arakia flow. I just proved that such convergence to some interesting object takes place, and was very proud during 2 weeks before I found that Arakia flow was initially invented in 1979 and then intensively studied. But this was a new result in 2005. But what is interesting? See the next line. My PhD student at this time, Tatiana Malavichka, proved the following statement. If you have that phi epsilon, it can be squared, it can be considered like density, like probability density. Suppose that it weakly converges to some discrete measure concentrated at points -1 and 1 with positive weights P1 and P2. Then the same holds. It is interesting, but if we just think a little bit, it can be understandable, because what it means that we leave the possibility of interaction for particles which are on the distance 2. But if we have two Brownian motion and we have no any special boundary condition, then it immediately leaves this, for example, level 2. This explains why we still have independence before meeting. Now, let me show you some stochastic analysis related to Arakia flow. Suppose that we have some partition of the interval in the space. I take interval 0, 1, for example. Take the moments of the first meeting for our particles abridged by the time horizon t. Then it occurs that the total time of free motion in Arakia flow is finite. So the supremum of such sum is finite with probability 1. So it does not depend on the initial partition. We can increase partition, we can take different partition, such supremum is finite. By the way, this result has a good interpretation in relatively to the end of the semester. At the end of the semester, students organize beer party usually, and what this result said. For example, we have a lot of students, everybody take a cup of beer, and just came in this crowd place up to the moment when suddenly somebody will hit your cup or something, some meeting happens. And the theorem says that the total time of such free motion is finite. And it leads to the following formal but interesting things. If we consider some integrals, it does not matter, stochastic or deterministic ds or dx us, one can also define the integral with respect to the flow of the interval. You see in the left-hand side of these two definitions, we have two signs of integral, but only one sign of differential. And this is not misprint. The another sign of differential, or the convergence of this infinite sum, infinite procedure, came from this tau u in the upper limit of the second integral. And then one can consider the following generalization of Kirsanov's theorem for stochastic flow. It occurs that if we consider the Arakia flow with drift A, here I considered initially the Lipschitz and bounded A, but nowadays with my former PhD student Nikolai Vovchansky produced a lot of things for more general drift. But if we consider the Arakia flow with drift, it means that every particle is not a Wiener process, but diffusion process with drift A and diffusion equal to 1. Then this new Arakia flow on the fixed interval has a distribution in the space of mappings, in the space of mappings, has a distribution which is absolutely continuous with respect to initial Arakia flow, and here you see density. Also, the space of linear combinations of such stochastic exponent are dense in the space of square integrable functionals from the Arakia flow. This natural statement which arises after we get the density, because Dolian exponent has a lot of faces, and one is the density in Kirsanov's theorem, another one is just a family from Ito-Wiener transform, and so on. So you see how the stochastic analysis can be moved from just one particle system, one Brownian motion, to the flow of Brownian motions. Also, here is the same. If we consider, it was proved in my joint work with my colleague, unfortunately she died already, Elena Ostapenko, that the family of time-scaled processes from Arakia flow satisfied large deviations with rate functions, and you recognize the same integral up to the moment tau. Now let us think about some semi-group of random operators related to stochastic flow. Why it is close to the subject which we discussed before? Because we already have seen that even in Harris flow, when we have a good interaction between particles, even in this case, the mappings in the flow can be discontinuous, can be like step functions. Then the natural question arises: how can we study geometry of such mappings? We cannot say anything about the derivative, about the curvature, about some things which are usual for differential geometry. So let us try to produce some machinery, and such machinery can be produced. If we move the function using our mappings, then function from L2R will go again random functions from L2R. So we will get the strong random operator, which is continuous probability linear map from the Hilbert space to the space of all random elements in H. You see some examples, and it is known, and it is so in our case too, that in general a strong random operator is not a randomly chosen bounded linear operator. It can be unbounded with probability 1. This is a very interesting remark from which Skorokhod create his well-known book, Random Linear Operators. And to understand this remark, one can think as follows. Usually, when we say random graph, random line, random something, we imagine a big set of such object, deterministic lines, graphs, or so on, and we imagine the probability distribution of this set, accordingly to which we just choose this object. But for strong random operator, it is not true. It means exactly what it is written in the definition. It is linear map from the space to the space of random elements. There are no good modification for every omega, which is bounded linear operator. Here is what we get if we will shift our function along the mapping from the stochastic flow. We will get the stochastic semi-group of random operators. They are equidistributed along the shift. They are continuous, for example, in square mean in the time zero. They are independent on disjoint intervals and have evolutionary property again. What can we say about the structure of strongly continuous stochastic semigroup? It occurs that sometimes one can get even stochastic differential equation for such semigroup, but in other case it is not true. We have to find something, and here let us consider the example. Let H be a Hilbert space with orthogonal basis, and we just consider diagonal random operators such that they kill almost all coordinates in positive time due to this condition on the series. And then we consider such finite dimensional projections. It occurs that they organize semigroup. But you remember we discussed that when we study stochastic flow, we have to find the noise related to this flow. This is a case when we can do this. Suppose that J be a semi-group of random finite dimensional projections. Then there exists an orthonormal basis and Poisson processes. So it must be organized exactly as I said. So if we have the semi-group of random finite dimensional projections, it has Poissonian noise. How to study this semi-group? One can consider the behavior of such well-known Kolmogorov-Witz for compact under this action of the semi-group, and get some asymptotic results like you see here. I see that my time is almost over, so I want to present something else, and will not say a lot about these results, but I just said that we can study widths of compacts under the semi-group transformation and get the asymptotic. Now let's came back to Harris flow and ask, okay, we have the stochastic differential equation. If they have a good coefficients, we cannot get Harris flow with coalescence. We cannot get Arakia flow as a flow of solution to this equation. So what we can do? Let us recall that we have Euler approximation to the stochastic differential equation. It is called sometimes Euler-Maruyama scheme. So let's try to do the same for Harris flow. Let us consider independent stationary Gaussian processes with zero mean and covariation function gamma, and consider such such recurrent equation. It must be said that we start from any point of view, u from R. Psi n have some gamma as a covariance function. Then one can say that such different scheme, as you see, will approximate Harris flow with the local characteristic gamma. So we can use this scheme, this Euler-Maruyama scheme, to approximate Harris flow. It is natural, but suppose we want that our gamma n has the following asymptotic. Define such a value, Cn, and suppose that it goes to 0 in this way. So it goes to 0, but slowly. Then endpoint motion converges to Arakia flow. You see, you need special condition 1 in order to get the convergence to Arakia flow in Euler scheme. It was proved by Nishenko in 2011. The same can be said about the convergence of the mappings. Also, I want to mention another one result, which belongs to my student at those time, Alexander Shamov, and which reflects to the complicated structure even of Arakia flow. You can consider the total deviation from the initial point for particles in Arakia flow starting from the interval 0, 1. Then it occurs that we have the following asymptotic at 0. You see, it contrasts to the law of the iterated logarithm, If we forgot about this soup, we will have just usual Brownian motion, and we have to get the iterated logarithm in the denominator. But now it occurs that we have the following result. The machinery for this result contains interesting generalization of Slepian lemma for family of martingales. So, summarizing my talk, I was trying to present you some troubles which we get when we want to consider system of interacting particles, some approaches which are developed at our department, and still we are studying different aspects of stochastic flows, equation with interaction, and so on. As I said, we have a lot of results. I just present you such which illustrate the features of these new objects. Now my time is over, so thank you for attention.
Thank you very much for your talk. And are there any questions? Well, I guess the talk was so informative that people need some time to feel that they have understood something. Okay, probably I have a question. You have mentioned that if the density of the joint characteristic in Harris flow tends to the indicator of 0.0, then we have in the limit Arakia flow.
Yes,
and
exactly.
There is also another result that instead of converging of this phi to indicator of the 0.0, one can take a convergence to a linear combination of indicators concentrated on +1 and -1.
Yeah, yes.
Can you clarify why the coalescence occurs?
Oh, it is the reason is following. The reason is following. Let me draw a picture here. Let me. You see, suppose here is two particles, and we have that they move this one. Then when they get this distance, as we said, the distance like 2 in this case, yeah, they must begin to be dependent, but they immediately leave this distance, yeah. So we have no troubles with this discrete measure concentrated not at the 0.0. But after this, when we have the meeting, we must have it because they are independent. After we have the meeting, this is a Markov moment, stopping moment for our system. And after this, we must have two Brownian motion. We already know that up to the limit we have order preserving case. So in the limit we will have order preserving case. So we must have two Brownian motions which are placed as I draw, so one under another, and have the same starting point. It is impossible. They must coincide. Yeah? There are no two Brownian motions which are placed one under another, have the same starting point. So after this, we have coalescence.
Okay, but can we find some other choices of this phi which?
Yes, surely. I had another former PhD student, Vladimir Fomichov, who proved that phi can converge to any discrete measure on the real line. So with some exclusion near zero. There are no point of concentration. Zero is not point of concentration of this discrete points. So there are a lot of different choices for phi in order to get Arakia flow as a weak limit.
Okay, thank you.
By the way, excuse me, I just add some comment because this result is one-dimensional. There is an article of Tom Kurtz and Peter Kotelenets related to two-dimensional and three-dimensional cases exactly of such kind. They also considered the equation exactly as I discussed. So we have dx epsilon equal to integral phi epsilon x epsilon minus p w big w capital dp dt, but in dimension 2 and 3. And due to the property that Wiener processes do not hit one another in this dimension, two independent Wiener processes do not meet one another at the same time in these dimensions, they get in the limit for mass distribution, they get in the limit usual heat equation, deterministic equation.
Okay. I have no idea what could be an analog of Arakia flow in many dimensions than our particles are.
You know, at least we can proceed as follows. I proposed such construction to Vitaly Konorovsky when he was my master student. At least we can consider Arakia flows relatively to different coordinates, independent.
Relative to what?
To different coordinates. So we can organize the flow as follows. We can organize the flow as follows, like x1, u1 t, and xn, un t. Yeah. Then if we take starting point u1, un, then this vector will perform a Brownian motion, of course, because it has independent Brownian coordinates. And in this case, we have a lot of coalescence and so on, so one can study, and it was a natural and interesting model. Okay, thank you very much. So, like a summary, all that we usually study in stochastic, it was like about one particle when we study Brownian motion or diffusion and stochastic differential equations. And now the idea is to lift all what we have, or not all, but something what we have, to the level of many particle systems, including interactions of particles, including singular interactions of particles like in the Arakia flow, when the particles are independent and then they meet and they stick together. And then additional technical difficulties arise, and one needs a lot of theory from stochastics and functional analysis, but there are a lot of things which can be done anyway, and it is interesting and have different interpretations. So on the language of flows with singular interactions, on the language of SDEs with interactions, and there was one third approach or first one which I don't remember. Related to random measures on the space of trajectories. I think it is also very perspective, but it contains even more than two mentioned cases, technical details which must be proved, must be constructed, additional construction, and so on.
Yeah, so there is a lot of there is a lot of works which can be done. So everybody is welcome to contribute. Yeah. So thank you very much for the talk. So if somebody still has some questions or remarks, you are welcome to say.
Thank you very much.
Thank you for your attention. Okay.
Okay. Thank everybody for coming, and the seminar is over for today, and see you next time.